Welcome back to the classroom. My name is Mr. Wong. Today we're going to be covering Module 8, From the Universe to the Atom. We're going to be covering Inquiry Question 5, Deep Inside the Atom, and we're going to be investigating this dot point here. So, like we said, we're investigating the standard model, and then we're going to try and explain some features about quarks, leptons, and bosons. Now, if you want to do a little bit of extra reading to supplement what we talk about today, that's your textbook reference. Just to get ourselves started, the concept of finding the smallest form of mass, we can talk about when we talk about in biology, we look at the size of humans and cells. That is quite small because obviously you can't see it. Cells are made up of molecules and atoms, so that's diving into the realms of chemistry. And then we go even smaller than that in physics, where we talk about things that are even smaller than the atoms, which we also denote as particle physics. Just to give you a little context, like we've been talking about quite a lot in different lessons, that how we've trekked all the way from going really small and then finding there are even smaller mass objects. These three gentlemen here, they came up with things that are smaller than the atom, the electron, the proton, and the neutron. We now know that the electron is obviously much smaller than the proton and neutron, but we also know that the proton and the neutron can be made up of other small components. So the proton is made up of both the proton and neutron are made up of things called quarks. Okay, we have 2 up and 1 down quark for the proton and 1 up, 2 down quark for the neutron. Let's talk about what quarks are. And that comes to the standard model of matter. So this basically governs, or this basically tells us all the smallest form of matter in the universe. This is the chart, okay? And just to give you a brief idea, we have our quarks and leptons. These borderline into a category known as fermions. Now, fermions are the elementary particles that make up the matter in the universe, so they provide the mass. So all the mass of the universe is provided by the combination and structure of these quarks. On the right-hand side, we have our bosons. These are force carriers or exchange particles. So we have the gluon, which generates the strong nuclear force. So that creates the binding of the nucleus between protons and neutrons. We have the photon. So that does the electromagnetic force. So that governs the electric fields, magnetic fields. You have the Z and W bosons, which generate interactions with the weak field here. So the weak force interaction with the Z and W bosons there. But we'll get into a bit more detail. And then the last one we have is the Higgs boson, aka known as the God particle. And this one allows for the interaction with the Higgs field. And that actually is the interactor that allows for our quarks and leptons to generate mass or to have mass develop in them. Okay, so let's go a little bit deeper. Like we said, this is what we're going to look into. And as we talked about, the quarks are the main building blocks into larger particles or larger to the subatomic and then obviously to the atomic particles. The leptons, they have a slightly different function, but they do govern the chemical properties of the elements of the periodic table. And then obviously we have our mediators of the force. Okay, so just to give you a little bit of detail, fermions come in odd half integers, so they can be half a spin, 3/2 spin. But what you just need to sort of understand with this concept of spin, it gives it the charge, so provides charge, so that's charge, and it also is the thing that gives these charged particles an intrinsic magnetic field. Remember, the fact that it is charged will indeed have a magnetic field. They belong, or they obey, what we call the Paulie's exclusion principle. The idea is that electrons of these kind of integers cannot be in the same location at the same time. So you cannot find two electrons both spinning in the same direction, in the same location to each other. They have to be different. The next one we have is the bosons, and they are force carriers, or they are the interactors with the particular fields, the four fundamental fields of the universe. And they come in whole number integer spin. You don't really need to understand what exactly spin is, but it's good to know that one is the half integer spin, one is just the whole integer spin, just to give you sort of a difference between the two. Okay, so let's look at the features of quarks. Firstly, there are 6 flavors, and what I mean by flavors is just 6 types. That's just how we call them. Each flavor will have its own antiparticle pairing as well. So quarks are elementary particles and are the fundamental constituents of larger forms of matter. They come in fractional charges, so you will find that something like an up or down charge or quark will have 2/3 charge, or 1/3 or 1/3 negative charge there corresponding. What we mean by fractional charge is that. We have strange charm, bottom and top. Now, progressively from generations, generation 3 is the heaviest. So, most heavy. And like we said, each one corresponds to a different antiparticle pairing there. If we actually look at the chart, up and down are indeed way smaller in comparison to the later generations there. You can even see the years in which they were discovered. Now, they can interact with the electromagnetic field, so they can interact with the photon. They will interact with the W and Z bosons, because these ones affect the radiation. So it comes down to the changes in the nucleus of the atom, that kind of stuff. We have the gluon, so that has the strong nuclear field, and that governs, the binding of the nucleus together. So this causes these particles to hold on to each other to form larger constituents. Now, these large constituents of quark combinations are called hadrons. Now, quarks only exist in groups with other quarks and are never found alone. These composites we call hadrons. Now, there's 2 types of hadrons. There are mesons, which are made from a quark and antiquark pair. And then we have baryons, which can be made from 3 quarks or 3 antiquarks. So as an example of a baryon, proton and neutron are types of baryons. So these 2 are baryons. Now, the proton is made up of 2 up quarks and 1 down quark. The neutron is made up of 1 up and then 2 down. So if we actually balance the charges of the individual quarks, the up quark has a 2/3 charge. The down quark has a -1/3. So if we add those together, we can find that overall the proton has a +1 overall charge, whilst the neutron cancels each other out to 0. However, given the fact that the neutron has an up and down, which one is positive, one is negative, you you can see where that distribution of charge is. So makes, if we're assuming these are there, that kind of explains why, although the neutron is overall neutral, it does have an intrinsic magnetic field because there is a distribution of charge from one corner to another. And then a type of meso is the pion, which is the quark and anti-quark pair. Now remember, these are highly unstable because anti-quark and quarks are basically particle antiparticles, and when that comes to be, they do eliminate each other. Okay, which of the following are examples of elementary particles? If you want to pause, have a go. If not, we'll go through the answer. So the answer for this one is D, quarks and leptons. Hadrons, remember, is a combination of quarks, which means that there is an internal structure. So it cannot be an elementary particle. So elementary particle, just recall, has no internal structure. In terms of the composition of a proton and neutron, B would be your answer, as we've spoken about. Okay, so hadrons are just a combination of quarks. They do have an internal structure. Mesons are made from a quark and anti-quark pair. They are very unstable because of that fact. Baryons are made out of 3 combinations of quarks or anti-quarks. And then we have the proton and the neutron as our examples of those. Next one we have is the leptons. Now they are quite small, or much smaller. They also come in whole number integer charges. So this group up here, you can split it. They have a -1 charge. This group here has a 0 charge, so they are, chargeless. Now the electron is probably one of the most well-known, or for you at least, the most well-known lepton out of the 6. And it has a really important function if we actually have a look. It governs chemical bonds, right? It gives the chemical properties of an element. So all the chemical properties of any element of the periodic table is dictated by the configuration of the electrons, but also the type of bonds you can form. It governs the ability to conduct electricity, absorb and emit light. That's how we identify the different structures of stars, knowing which element matches with what. So it really has quite a lot of use. Okay, so they are probably the smallest in terms of mass, for elementary particles. They don't experience the strong nuclear force, which means that they tend to be, in solidarity most of the time. You can split it up into 2 categories. You can have the charged leptons. The electron is the least heavy, and then we get to tau, which is the most. They are also -1 charges. The leptons that have no charge are basically the neutrinos. They are very hard to detect, and they also have very little mass. But also, don't forget, the reason why they're hard to detect is because there's no charge. So there's not going to be any ionization going on there. Okay, as you can see, these ones are a bit more difficult to find, because what you can see is the time it takes to actually discover these were a lot more difficult than when it came to the quarks in that sense there. What we also talked about is the neutrinos have basically a 0 mass, so that's also the reasoning there. In terms of the interactions with different fields, only the charged leptons will interact with the electromagnetic field. It makes sense because they are charged. These ones down here are not. Actually, in this case, both charged and non-charged leptons will interact with the weak field, so it causes decay, and we'll show you a form of where one of these leptons will decay into another. None of them interact with the strong field, and only the electron, muon, and tau interact with the Higgs field to generate mass. Now, we did say that neutrinos generally have a negligible mass, so it might have a little bit of mass, but to our understanding as of now, it has nothing to do with the Higgs field. And we don't really know where it is coming from at this point in time. So, lepton decay. Heavier leptons tend to decay into smaller leptons or lighter leptons like mu and tau, you can see. Mu is decaying into an electron. In that process, you will get the neutrino version of that lepton to come out. So we have the electron neutrino and then the muon neutrino coming out like that. In an application, they actually use lepton decay, for example, in the Fukushima crisis, to determine the location and amount of nuclear fuel that was damaged. So it does have its applications. So if we compare the pair, we've talked about the two fermions. We have the lepton, the quarks. Okay, remember the leptons come in whole number integer charges or no charge, while as quarks come in fractional charges. If we then go through some multiple choice, let's go through C. The fundamental particles which make up the matter we can see are, in this case, up and down quarks, electrons and electron neutrinos. Makes sense because these are the ones that form the atoms and the elements of our universe. Which of the following is a hadron? That would be a meson. So there you go. So next one we have, as we do a quick summary, quarks and leptons. They are fermions. Quarks will interact with the weak field, the electromagnetic field, and the strong nuclear field to produce hadrons like protons and neutrons. Okay, so these are the things that will create larger entities. Leptons, they will interact with the weak force and the electromagnetic force, but it doesn't interact with the strong nuclear force. So it's not going to combine to make a larger constituent. Okay, so we've covered quarks, leptons, hadrons. Let's look at bosons. Okay, so let's kind of have a look at what each one does. The photon is the force carrier for the electromagnetic field. The W and Z bosons are the carriers of the weak field. Remember, the weak field governs, radioactive decay, those kind of things there. The gluon is the carrier for the strong field, and the Higgs boson is the field that everything wants to interact with in order to gain mass. Okay, so when it comes to the four fundamental forces of the universe, we have gravitational force, electromagnetic force, the weak nuclear force, and the strong nuclear force there. Remember, the strong nuclear force holds the quarks together to form hadrons. Okay, you can also contribute that as ensuring stability of the nucleus. So ensures stability of atomic nucleus. We have the WZ bosons, so they interact with the weak nuclear force that's responsible for the decay of quarks and leptons into lighter quarks and leptons. So, radiation. That's quite immediate to that. Now, the additional part to it is the W, or the two W bosons, they're both charged, so they actually also interact with the electromagnetic field. Now, as a consequence, because it can interact with the weak field and the electromagnetic field, the W boson has a interesting field reaction, which we call the electroweak field. So it can interact in both ways. The photon just interacts with the electromagnetic field. And then we have a theorized one called the Gravitron. Now, I wouldn't recommend you needing to remember this one because we haven't actually discovered it yet. But if we do, it will tell us the existence of, or the reasoning of the gravitational fields in all that kind of sense. Okay, so in the 1970s, two scientists predicted the weak electromagnetic force within the standard model of matter. The idea of this implied that electricity, magnetism, light, and some types of radioactivity are manifested by a single force known as the electroweak force. Now, this makes sense with what we talked about at the start of the Big Bang cycle. If you recall, the electroweak force was the second force that branched out just after when the Big Bang event occurred. There are some complications with their idea. The reason being that this model would predict all particles should emerge without any mass. Now, the only particle that does that is the photon, but the W and Z bosons do have mass, and also quite heavy at that, 100 times that of a proton. So the question lies, how does these bosons generate mass? How does it generate mass for the other elementary particles? And that's when the concept of the Higgs boson came in, aka we also call it the God particle. The reason why the W and Z bosons were able to attain mass was because they interacted with an invisible field known as the Higgs field. Okay? And like I said before, the Higgs field wasn't discovered until 2013, so it's quite a long wait in between. How do we explain something getting mass in the Higgs field? Now imagine you're in a party and you see a celebrity that comes through. Okay, now the idea is once you see the celebrity, crowds of people will flock to the celebrity and they kind of surround the celebrity that way. So it's in this process that mass is being gained around the celebrity. So that's actually how it's seen as what the Higgs boson does. It allows for the interaction of particles to come together within the Higgs field to increase its mass to get and obtain mass overall. Okay, so that's how the Higgs boson allows for the attainment of elementary particles to have mass. The longer this interaction occurs for, the heavier the particle will become, or the substance will become. And the reason why the photons don't have mass is because they don't interact with the Higgs field. Okay, so that's what the Higgs boson does for us. Okay, so that kind of nicely summarizes everything we've talked about. We've talked about matter as something that has mass. We said that atoms are the simplest forms of things that have chemical properties. Smaller than the atom, we have the electron, proton, and neutron. And we also know, whilst the electron might be an elementary particle, the proton and neutron are hadrons. They're made up of a combination of quarks. And the quarks and the leptons are the smallest form of mass you can find in the universe, at least at this point of our understanding. Are there any complications? Are there any limitations? There are. The first thing is it doesn't work well with Einstein's general theory of relativity. There is no unification of force involving gravity. Obviously, there's no gravitron. At least not for what we know now. The standard model is a quantum mechanical model, while general relativity is not. So how do we bridge the gap between those two? There's no reason why specifically we have 6 flavors of quarks and leptons. So there's no explanation why that occurs. And it doesn't account for antimatter. So how does antimatter exist there? The last one we could probably say is there a sort of fusion combination of a lepton and quark, as in a leptoquark? We don't know that either. So where is this model useful? Well, it is incredibly useful because it helps explain the formation of all these different particles and obviously the combinations of the forces and the different arrangements of the periodic table. It explains what happened in the Big Bang and how these elementary particles were able to acquire mass and then obviously generate the atoms, the periodic table elements, and then stars. And it's really good at allowing us to make predictions of the type of particles we could find when we have them collide in a particle accelerator. Now, this we're going to talk about next lesson, the function of a particle accelerator, but that kind of tells you what's happening there. So, sort of to show you how far we've come, we went from 400 BC, where a guy predicted that if you can't break anything any smaller. And then we had a guy just before J.J. Thomson in John Dalton proving the existence of the atom. Then we have Thomas showing that there are things smaller than the atom, known as an electron. We had Rutherford with the proton, Bohr, Chadwick with the neutron, and then all the way into the 1970s, we had the Standard Model of Matter. And don't forget, in 2013, that was when we finally discovered the existence of the Higgs Boson. So hopefully that kind of explains to you everything you need to know when it comes to the Standard Model of Matter. There's quite a lot of detail, and hopefully you were able to get a better understanding of how each component works with each other. Remember, there are fermions, bosons. In terms of fermions, you have two types, leptons and quarks. Combination of quarks makes you the hadron. And that concludes the lesson for today. I'm Mr. Wong. See you next time.